All right, well, welcome to Wednesday, our second to last Wednesday of this course. If you can believe it, we're already up to that point. So today's plan is actually going to be to review for the exam that we're having on Friday. We're doing just perfectly we're on schedule, everything's great. We only have 2 more sections to do that we'll be able to knock out next week. So we're going to spend today talking about the exam and kind of getting you ready. We're going to go over the quiz from last time. I'm not actually done grading it. Some of them I've done, but not all of them. But I still want to go over them since that stuff's going to be on this exam. And that'll be good review, at least for the first couple sections as well. So we'll do that. But before I get into what my plan is, are there any questions that you guys have? Any homework you want to look at or anything like that? All right, well, hearing none and seeing none, let's go ahead and talk about the quiz. So the quiz, for the first question on the quiz, and I don't know if you guys have it available to see. Actually, you know, I think I've got it up. Let me share it real quick. Okay, so hopefully you can see my screen here that shows the quiz. So we'll start with these two. We've got number 1 says, use differentials to approximate the value of natural log of 0.9. And Ollie, just so you know, I did see in the chat, you say you're finding one. I'm assuming that means a homework question. When you get it, go ahead and just throw it into the chat and we'll come back to it, okay? All right, so for number 1 here, it says use differentials to approximate the value of the natural log of 0.9. Okay, so for this one, differentials, those are the little dy, dx stuff. So what we're going to do is we're going to take the function natural log and we are going to evaluate it and its derivative at a point somewhere near what we're interested in. And then what we're going to do is use that derivative. So we've got a linear approximation for the function. Use that derivative to approximate. Okay, so here's what we're looking at. We're basically looking at natural log of x. And we want to know, hold on, sorry about that. We want to know the natural log of 0.9. All right, so let's choose a point near 0.9 that we know. I'm going to use 1 because I know the natural log of 1, and you guys should know that too. The natural log of 1 is 0. Log of any kind of log of 1 is equal to 0. So we're off a little bit, but we're going to use natural log of 1. So this tells me then that my delta x, and when we do this with differentials, the delta x and the dx are exactly the same. But that's going to be a minus 0.1, right? Because we're off from 1 to the point where we're looking at, we need to go back 0.1. Okay, so what we know then is the change in our function, delta y, is approximately equal to f prime of x times delta x. All right, so let's look at this f prime of x. So natural log, its derivative is 1 over x. So if we evaluate that at 1, we also get 1. So delta y is approximately equal to 1 times negative 0.1, which is negative 0.1. So what we know then is that our natural log of 0.9 is negative 0.1 away from the natural log of 1. Okay, so it's going to be the natural log of 1 plus negative 0.1, which is 0 minus 0.1, or negative 0.1. So the natural log of 0.9 is going to be around negative 0.1. All right, well, because I know you're all desperate to know, I just use my calculator right here and get the natural log of 0.9 is negative 0.10536, blah, blah, blah. All right, so from the calculator, natural log of 0.9 is negative 0.10536. Dot, dot, dot. All right, so pretty close, right? We're off by 5, what is that, thousandths? That's pretty good. All right, so there was question number 1. Any questions on that one?
Not on this one, but pertaining to the quiz on Canvas, when I tried to look this morning, I still saw that my quiz score wasn't posted.
Right, that's what I said. Not all of them are graded. Yours is one that's not graded yet. So that'll happen most likely later today.
Thank you. Yeah, take your time.
For sure by noon tomorrow. That I'll have all of those things posted so that you guys know how you did. All right, so good for number 1. All right, so let's go take a look at number 2 then. We'll go back to the quiz. Okay, so for number 2, it says use differentials to find the relative error in the volume of a spherical baseball if the radius is measured to be 3.65 centimeters with a possible error of 0.1 centimeters. All right, so I put here use differentials so that you use calculus. So you didn't just actually add 0.1 to the radius and subtract 0.1 from the radius and then calculate the change in the volumes, right? Even though that we could use do to find relative error as well. But we're just trying to approximate. We're trying to be a little bit faster this way. So we're going to use differentials for the baseball. So what we need to do is get a formula that relates the volume of the baseball with the radius of the baseball. And then once we have that, we differentiate and we do basically what we did in number 1 to find our potential error. But again, this is asking us to find relative error. So relative error is going to be the absolute error divided by the true value. All right, so let me go back to the whiteboard. All right, so for this one, we need the volume of the sphere. So you can either, if you know that, cool. If not, you can look it up. It's 4/3 pi r cubed. So we need to know dV. So if we do dV dr, take a derivative of v with respect to r, we're going to get 4 pi r squared. Right? The 3 comes out front as a multiple, cancels with the 1/3, and we decrease the exponent by 1. So dV is 4 pi r squared dr. All right, so this is enough for us to go ahead and calculate the error in the volume. We just need to know the radius, and we need to know how off we are. The d's, these little guys, the differentials, the dr and the dv, those are the actual errors in the quantities, right? So dv is our error in volume, dr is our error in the radius. So if we know the radius and we know our error in the radius, we're good to go. And we have those numbers. We were told r was 3.65, and we were told that the dr, we are off by 0.1, potentially 0.1. So we've got enough to find that. Now I'm actually going to do one more step before I plug stuff in. Since I want because this is the absolute error, but what I want is relative error. And so for the relative error, that's going to be dV, that error that we just found here, but divided by the true amount. So I'm going to go ahead and just do that real quick before I start plugging stuff in, because you're going to notice that lots of stuff cancels. What we're left with is a 3 dr over r. So pretty clearly you see the pi's go away, the 4's go away. With the r's, these two r's cancel with 2 of them on the bottom. And that 3, since it was a fraction on the bottom, that's why it flips up to the top. Anyway, so I did this first just because it's going to be quicker, a lot easier in terms of stuff to plug in. So we're going to get our error in the radius was 0.1 centimeters. The actual value of the radius was 3.65 centimeters. So you can do that division. And the number that I got when I plug that into my calculator is 0.08219 blah, 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 or 8.22%. So if we have this kind of a mistake in terms of our radius, being off by 1/10 of a centimeter, it's going to lead to about an 8.22% error in the volume.
Did we have to write it as a percent? Because if
No.
it just
No,
Okay.
If you just wrote it as 0.082, that's fine, right? Because percent is just another way of writing it. Now, if you wrote 0.082%, then that's incorrect, right? But
different answer, yeah.
Yeah, these two numbers are the same. And so if you give me the first one, that's full credit.
Great, thank you.
You're welcome. All right, other questions on this guy? No? All right. Okay, so let me show you the third question on the quiz, which is the one that you guys definitely liked the least. Good old related rates question. So for this one, it says we have a 15-foot long ladder resting against the wall. The bottom of the ladder is being pulled away from the wall at a speed of 2 feet per second. The question is, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 4 feet from the wall? Okay, so this is, you're up on the ladder, hanging up the Christmas lights. Although I guess for some of us, we're a little bit behind schedule if we're just doing that now, seeing, as soon as Halloween ended, it became Christmas or something. Anyway, so you're up there, you're hanging your lights, and the bottom starts slipping away because the ground's a little wet or whatever. So the question is, how fast do you start falling? All right, so this is a related rates question. And the way that you can tell is we're being asked for a rate. When it says how fast is the top of the ladder sliding down, that's a speed. And a speed is a rate. It's a rate of change. We also have another rate of change. It says the bottom of the ladder is being pulled away from the wall at a speed of 2 feet per second. So we're being asked for a speed. We're given another speed. Those are both rates. So that means this is going to be a related rates question. All right, so let's go to the whiteboard. So I'm going to start by drawing a picture. So we've got the ladder that's resting up against the wall. And then we got the ground down here. Okay, so I'm going to assume that the ground is level, and that's an okay assumption here, even though I didn't state it Usually that's the case, but this is our situation, right? So here's the picture. Let's put on the things that we know about in terms of falling, the rates of change. So we're looking for how quickly is the top falling, which means in terms of a quantity, that's changing, we're basically looking at the change in the height, right? If the top of the ladder is falling, that means that h is decreasing, and we're looking for how quickly is h decreasing. All right, and then we're also given how quickly the bottom is being pulled away. And so in terms of a quantity that's changing there, I'm going to go ahead and call it x. We've got this guy x. X is increasing because the bottom is going away from the wall. So in this context, we've got then dx dt is 2 feet per second. Right? The bottom is being pulled away at 2 feet per second. So that x is increasing at 2 feet per second. The dh dt, that's what we're trying to find out. So you notice I didn't put any numbers or anything here on this picture. I don't want to do that yet. When I do these, I like to first just put the quantities, try to get variables to show the things that are I'm either trying to find or are being told. So now I need some sort of relationship between x and h. And it's pretty clear from this, I want to use the Pythagorean theorem because I know that x squared plus h squared is going to equal the hypotenuse squared. And that we actually know. That was 15 feet long ladder, right? It's 15 feet. So we're going to have 15 squared. So if you square out 15, you get 225. All right, so if you remember what I told you for my process with related rates, or what you need to do, figure out the rates, both that are given and that you're looking for. Okay, so I did that. Then get an equation that relates those things. And that's this step right here. Now we're ready to differentiate. So we're going to take a derivative with respect to t. So we have to use implicit differentiation. So we're going to get 2x times dx dt plus 2h times dh dt. So those both came from the chain rule, right? It's power rule, but then chain rule gives us the dx dt and dh dt. And then the 225, its derivative, of course, is 0. So let's solve this for dh dt before we plug in numbers. So I'll just slide that 2x dx dt onto the other side. And then I'm going to divide by 2h. So the 2's cancel. And so we end up with dh dt is equal to minus x over h times dx dt. So in order to know how quickly the top is dropping, I need to know how fast it's being pulled away. And that should make sense, right? If we pull if the bottom is moving faster, we should expect the top to move faster. The bottom's moving slower, we should expect it to move slower. So it depends on how fast that's moving. But this is a little bit weird. You may not expect this, but it does also depend on x and h. It depends where the ladder is at that moment. Basically, it depends on the angle. Because the steeper this is, the slower it's going to drop. If it starts getting kind of flat, it drops very quickly. So that's what ends up happening here. All right, well, now we're ready to get this. So let's see. So dh dt is going to equal. All right, so we need minus. We need to know the x. So we were told x was 4 feet. We need to get h. We'll get that in a second. But then the dx dt is 2 feet per second. So the question is, what is h? Well, we're going to get h from this equation right here, from the Pythagorean theorem. We'll plug in 4. So we're going to get 16 plus h squared equals 225. So h squared equals 209, or h is plus or minus the square root of 209. But this one clearly needs to be a plus because we don't have a negative height. It's not underground. So that's going to be the square root of 209 feet. So the feet's here cancel. We're left with feet per second, which is what we need. So we got -8 over the square root of 209. And you probably would rather have this as a decimal, which is totally cool. If you left it as -8 over root 209 feet per second, full credit. But most of you went to sort of a decimal, which is fine. And so we get -0.55 feet per second. So at that point up there, you're dropping at just over half a foot a second. And you're going to speed up as you go down. All right, so there's that guy. So with related rates questions, again, there isn't a always do it this way, because a lot of it depends on what equation do you get, what relationship do you have. And this is the hardest part, no doubt, getting to what is the equation that relates them. So read it carefully, draw pictures, things like that, and that can help. All right, so there's question number 3 on the quiz. All right, so any questions on that one? Anything I can help you with here? All right, so like I said, look for those scores to be in probably later today, if not for sure by noon tomorrow. All right, so with all of that, Alia, did that give you enough time to figure out the homework you wanted to look at? All right, so from the 4.6, she wants to look at numbers 8 and number 13. All right, let me write those down here real quick. Okie dokie. All right, so let me real quick switch my share to that screen, and we'll take a look at those. So these are the limits at infinity and asymptote section. All right, so hopefully you guys can see my screen as it's still pulling up. All right. Well, while I'm waiting for this, Ollie also just asked me in the chat if exam scores are in. They should be. If yours isn't in, let me know, and I'll double check that because I did get those graded. But I know that sometimes Canvas is a little bit wonky, so you can just send me a message or something and let me know. But let's see here. So questions 8 and 13. All right, so here's number 8. All right, so this one just says evaluate the following limits, and if needed, enter infinity or minus infinity. All right, so looking at these, since they're fractions, what I want to do is I want to look at top and bottom, and I want to think about what's the biggest term in both the top and the bottom, right? Because that really tells me what goes on as we go towards infinity. So if we look at this guy, on the bottom, it's pretty easy to see. It's just plain old x. On the top, you might be tempted to go, ooh, it's an x squared, but it's not really an x squared because that x squared is inside of a square root. So really, that's behaving like an x. It's behaving like the square root of an x squared. So in terms of the top and bottom of this thing, they're both being driven by the x term, either the square root of x squared or the x itself. So that actually tells me I'm going to get a finite number with my limit. Okay, so let me show you the old way of doing this, and then I'll show you the fast way of doing this. Okay, so let me go to the whiteboard. Let me go ahead and clear this off. Okay, so here's our function. We're looking at the limit as x goes to infinity, square root of 6 plus 7x squared over 11 plus 10x. Okay, so here's what we did algebraically. You may remember seeing something like this, like I think it would have been last week at some point. If I start with the top, I can pull out an x squared on the inside. So I have x squared times 6 over x squared plus 7. That x squared can come out of the square root. So I'm still taking my limit as x goes to infinity of x times that square root. Let me bring it down here so it doesn't look like it's an x root. And then what I can do is I can factor out an x out of the bottom as well. Actually, let me do that while I'm here. If I factor out an x out of the bottom, I get 11 over x plus 10. And now those x's cancel. And I'm ready to take my limit. So as x goes to infinity, the parts with the x on the bottom go away. Those go to 0. So I'm left with the square root of 7 over 10. So that was the algebra way of getting to this limit as x goes to infinity. So it's root 7 over 10. The other part of the question was, what's the limit as x goes to minus infinity? And that one's actually going to be negative root 7 over 10. Algebraically, we would have done it the same way, but the reason that this is going to minus root 7 over 10 is if you look at the original, the square root is always positive. The denominator, that one can be positive or negative depending upon which way we go. If we go towards minus infinity, this is negative. So a plus over a minus gives us a minus root 7 over 10. And that's because technically, when we pull out that x, it needs to be in an absolute value. And the absolute value of x over x is either 1 or negative 1, depending upon which side we're in. So up until Monday, this would have been how we'd have done these problems, or done this problem. But now we have another way. We've got L'Hopital's rule. So check this out. Actually, before I go to L'Hopital's rule, any questions on what I did here on this algebra?
I think I was just a little bit confused about what went back to the original form of it for negative infinity instead of using what you'd already set up for positive infinity.
Okay, well, so again, with the technically, there's this absolute value. When I factored out, like it's really easy not to do that when you're doing the algebra. And with the positive infinity, you don't have to worry about that because if x is positive, this is still positive. The reason I don't do it when I do the algebra is because it gets confusing. If all of a sudden I throw in absolute values, people start going, wait, what? Where'd it come from? And then trying to divide an absolute value by something that's not an absolute value is confusing again, right? So that's why I don't do it. I just factor out the x and I cancel. But what I remember is that when you pull stuff out of a square root, there's the potential that you change the sign. That potential changing of the sign is what makes me go back and look at this original one and just think about it in terms of what kind of signs do I have. So if we had done the algebra properly the entire way, brought out the absolute value, and then realized that canceling the absolute value of x and x gives you either +1 or -1, then we wouldn't have had to go back to the original function. I personally would rather just real quick look at that first thing and look at the signs, because that's easy. That's actually really easy, right? Like square root, always positive. Done. Square roots are always positive. So you don't even have to think about those. So then you just look at this bottom thing, 11 plus 10x. What kind of sign does that take on? That's actually also really easy to see as you go towards infinity. Just look at the highest power and just look at, well, what happens to that? 10x. If x is positive, that's positive. If it's negative, it's negative. So for me, the whole positive negative thing is fast, it's quick, it's easy. And so I use that as my determination whenever there are square roots involved. If there aren't square roots involved, everything works out. You don't have to do that. But that's because of the simplification. When you pull stuff out of square roots, it is extremely dangerous. Extremely dangerous. In fact, that's one of the reasons why we never teach you to do that. Like you think about it, how often do you pull stuff out of square roots that are not numbers? Virtually never, right? All the simplification usually happens inside of a square root. And that's because pulling stuff out is dangerous. If it's got letters, you potentially change the signs, which can completely change everything.
So I understand how you got the signs there, but then if you're plugging in negative infinity to that original one, how do you end up with square root of 7 over 10 at all? Or I guess negative square root of 7.
The negative isn't from the square root of 7. The negative is coming from the bottom.
But how do you end up with those numbers? Like, I understand if you go all the way through the process for positive infinity, how you end up with real numbers for your answer. But if
Uh-huh.
I'm just confused about if you go back to the original and plug in negative infinity there, how that doesn't just like get rid of your actual values.
Okay, I don't think I quite understand, because if you plug in negative infinity, you're going to get infinity over infinity, right? Because you're going to have 7 times infinity squared plus 6 is huger than huge. Take the square root of that, it's still infinite. So plugging in would give you infinity over infinity.
Yeah, I think that's why I'm confused.
Okay, but that's why we do the algebra, right? Whenever we got infinity over infinity, we had to do some algebra. And the algebra we did, like all of these steps are exactly the same, whether we're going to infinity or minus infinity. The only difference between going to plus infinity and minus infinity is how the canceling or the simplifying of these guys, the x's, behaves. That's the only thing that's different. And whenever you have absolute value of x over x, it's equal to +1 or -1, depending upon where we are. So the only difference is it's either going to be plus or minus. It's either going to be positive or negative.
Okay, so if you've already solved for positive infinity, you can assume that it'll be either that or negative that.
Yeah.
Okay, gotcha.
Yeah, and it's not I can assume that, I know that, because I know how this stuff simplifies, right? That the algebra is the algebra. It's just in this case, it's either the positive or the negative because of the fact that the sign's the only thing that might have changed.
Okay, thank you.
All right. Okay, cool. But now check this out. So after last class, we now have another way that we can approach this. We can use L'Hopital's rule, right? Because when I plug in infinity, I get infinity over infinity, which means it's just begging for L'Hopital's rule. So let's check out what that does. So remember, L'Hopital's rule says if you get infinity over infinity or 0 over 0, you can actually get the same limit if you look at the derivatives. Okay, so let's differentiate. So on top, we're going to get 1/2 times 6 plus 7x squared to the minus 1/2 times 14x. So that's chain rule. Remember, the square root is a 1/2 power. So that's the half that comes out front. We decrease by 1, and then we have to multiply by the derivative of what's inside. On the bottom, the derivative of 11 plus 10x is 10. So let's simplify that real quick. So the 14 divided by 2 is 7. So we're left with 7x over 10 square roots of 6 plus 7x squared. And we can actually do the same thing here where we factor out that x squared on the bottom. So we're going to get 10x over the square root of 6 over x squared plus 7. We'll cancel those x's, but remember that that means it's either positive or negative of this. And now if we plug in, if we go to infinity, we're going to get 7 over 10 times the square root of 7. And 7 over root 7 is root 7. So you can use L'Hopital's rule as well. Gets you to exactly the same place. But notice again, It's root 7 over 10, but there's the potential of the plus or minus because I factored out that x squared. Anyway, so you don't have to do it that way. It's another option. You can use L'Hopital's rule. All right, so good for that one. Any other questions regarding that guy? Okay, so let me hop over to the homework again. We'll look at what the other one was. Number 13. Okay, so this one now we want to evaluate the following limits. And again, if needed, enter infinity for or minus infinity. All right, so we're looking at the limit as x goes to 11/4 of 16x over 11 minus 4x. And we're just looking at the two limits, so the one-sided limits. All right, so let's go back to the whiteboard. And let's try those guys out. All right. So we're looking at the limit. Let's do the first one here. Limit as x goes to 11/4 from the right. 16x over 11 minus 4x. So again, the first thing we should do is just try plugging in 11/4. So if we plug in 11/4, we're going to get 16 times 11/4 over 0, which is 44 over 0. And so this actually tells me something right away. What this tells me is that this is going to be plus or minus infinity. Now, it can't be both. It's got to be either plus or minus, but it's going to be one or the other. So what about this form tells me that?
The 0 as the denominator.
Yeah, the divide by 0. If you ever have a non-zero number, so like in this case 44, you ever have a non-zero number divided by 0, you know it's going to be infinite, either plus or minus. All right, now the question is, which one? Well, I'm going to go back to this guy and I'm going to think about what kind of values do I get in terms of the signs when I'm to the right of 11/4. All right, so thinking about the signs, the top is going to be positive because I got 16 times a positive number. I don't care what that number is, it's going to be positive. All right, on the bottom, if I have a number bigger than 11/4, then my denominator is going to be negative. Try something slightly bigger like 3, right? 3 is a little bit bigger than that. If I were to plug in 3 on the bottom, I get -1. So I get a positive divided by a negative. Okay, well, positive divided by a negative is a negative. So now remember with the plus or minus, it's not an or anymore. I know this goes to minus infinity. So there's that guy. Now, if I were to look at the other one, now I'm coming from the left. Here's the beautiful thing. I've already done all the work I need to do. I already know it's going to go to either plus or minus infinity. The only question is, which one. So I'll do the exact same thing with the signs. On the top, it's going to be a positive. Because again, 16 times a positive number is positive. Don't let this little minus here throw you. It's not a negative 11 force. It's just we're coming from the left. So it's still going to be a positive number, right? It's going to be very close to 3.75. Or sorry, 2.75. All right, so the top is positive. Now at the bottom, if I put in a number smaller than 11 force, like 2, I'm going to get a positive number. So in this case, I get plus over plus, which is positive. So that means I know that this one's going to go to positive infinity. So on the graph, like if you were to look at the graph of this thing, I've got an asymptote at 11 force. So I've got a vertical asymptote at 11 force. And I know what's happening on either side of this. On the right, I'm going down towards negative infinity. And on the right, I'm going up towards positive infinity. Now, what the rest of this graph looks like, I don't know. But we could do the calculus on it, right? We could look for, well, we could do non-calculus. We could find intercepts, look for symmetry, and stuff like that. We could go to the calculus to figure out increasing, decreasing, and concave up and concave down, and stuff like extrema and inflection points. Excuse me. And then we could put that all together. But at least I know that at 11 force, this is the story. I'm going down on the right and up on the left. All right, so is this one better for number 13?
Yeah, and you just knew it was plus or minus infinity because you knew that it couldn't exist there. Is that right?
Yeah, because I'm dividing by 0. Anytime you have a non-zero divided by 0, you know the limit's going to be infinite.
Okay, thank you.
It's just a question of plus or minus, and that's where you have to go back to the sign idea. All right, cool. All right, any other questions on homework stuff? All right, looking like we're good there. So let me go ahead and switch. I'm going to go up to the whiteboard because my back's starting to get a little stiff from sitting. And we'll kind of talk about the remaining or review for the exam, the other sections and stuff we need to look at. So give me just 1 second here and I will see you in a moment. All right, so exam on Friday. First of all, let me just remind you what it covers, what the different topics are, and what you're going to need to, and then we'll talk about maybe specifically what you need to do for those different sections. So this is primarily a chapter 4 exam. It's not the entirety of chapter 4, right? We're still in chapter 4, but it's going to start back with 4.1. And so that was related rates. Okay, so that's your first topic, big topic on this exam. So think about the quiz that we just went over, that example with the ladder falling against the wall. Related rates questions. Think about their word problem, right? It's going to be a word problem. You're going to have to sift through it. So think about the general techniques that I've shown you. Start by figuring out what rates do you know and are you looking for, and use the words. right? Like a lot of times it says rate, right? The pile of dirt is growing at a rate of, right? Or the population is decreasing at a rate of, right? So a lot of times they use the word rate. That's a giveaway, right? You see that word, that's a dead giveaway. Another word to watch for is per. If they ever give you units that are per, miles per hour, feet per second, right? Dollars per hot dog, like whatever. You see that word per, think, ooh, that's a rate. Because per means to divide. And think about with our rates, it's always something divided by something else. Okay, so that will help you recognize what the different rates are. Then you got to build the equation. And that's where it can get a little challenging, but we've seen some things that are pretty common. Right triangles show up a lot. And with right triangles, Pythagorean theorem should pop up in your head. Don't forget other things like the trig functions, right? Sine, cosine, tangent, sometimes those are useful, especially if we want to relate some sort of an angle in there. We've seen similar triangles where we get ratios of sides of similar triangles are equal. We have all the geometric formulas, areas, volumes, things like that. Since this is basically an open book kind of test, don't hesitate to pull up, Google and be like, what's the formula for volume of the sphere? Right? Like if you don't remember it, you don't remember it. That's okay, but go ahead and find those things. But then once you have that equation, then you know what we got to do. We got to differentiate implicitly with respect to t, and then put in all our information. Okay, so another warning I'm going to give you about related rates is watch your signs, your plus or minus signs. Remember that if something's decreasing, the rate is negative. So you might have a case where a quantity is decreasing. Make sure you put the minus sign in there, because otherwise you can end up with the wrong numbers, with the wrong value. Okay, so related rates are going to be on there. Guaranteed you're going to get a related rates question, right? But use that to help you kind of figure out how the process. Okay, after related rates, we talked about differentials. And for differentials, there were a lot of things that we did in differentials, just to remind you, just in case you're like, wait, what's a differential? These are the dy, dx, etc. Those are little differential things. And what we use those for, we did linear approximations. So a good example would have been, is that one on the quiz that was it the natural log of 0.9 or whatever it was. And what we were doing there is basically using the tangent line as our approximation for the curve, because that made it a lot easier. So I did examples in class of like a square root function. You could use exponential functions, log functions, it doesn't really matter. But basically the goal with those, if you're going to approximate, is you want to find a point that's close to the one that you're looking at, right? Like in that quiz example, we were looking at natural log of 0.9. So we found a point that was near 0.91. That was easy to plug in, that we knew the value for. So start with a point that you know that's close, and then use the line. And it's super, super easy because the formula is always the same. Delta y is approximately equal to f prime of x times delta x. And the difference, because I know that sometimes this pops up too, the difference was that the delta y, this is the actual change in the function. And the dy, because dy is exactly equal to f prime of x times dx. The dy is the approximate change. Or you can think of dy as the change in the line. So again, we're using the line to approximate the actual change in the function value. And the smaller our step, the smaller our dx or delta x, those are the same thing. The smaller that number, the closer these approximations get, right? The more you zoom into a curve, the more linear it looks. Okay, so we did linear approximations in this differential section, but we also did error propagation. I'm going to put here errors. And so it was really the same idea. It's just now these delta x and delta y. I'm going to put your delta x, delta y, etc. are the absolute errors. And so when I put absolute, that just means that is the amount of error in our thing. So go back to that quiz question. Like when we had the error in the radius, the 0.1, that was our delta R. Delta V, that was the error in the volume, right? So these are our absolute errors, but be on the watch for the fact, make sure you read carefully, because sometimes the question will ask for absolute error, sometimes will ask for relative error. So just to remind you about that, excuse me, the relative error it's equal to the absolute error divided by the actual value, or actual amount. So if it asks for relative error, there's one more step to do. You need to actually go ahead and divide that absolute error by the true amount. So that's what we did on a quiz, right? We were looking for the relative error in the volume. So I took the dV and I divided by V. Okay, so that was 4.2. 4.2 was really getting at using the lines to approximate what was going on. All right, so that stuff should feel pretty good or fresh, both of these sections, just because we just went over those in the quiz, right? But of course, once we kind of get through the list of everything, if we want to come back and visit this, we can. Okay, so then the next section, so that was 4.2. 4.3 was all about increasing and decreasing, or and extrema. So the next thing we hit on were extrema. Now I'm going to kind of combine this into a couple of things, or a couple of sections, kind of all get in here. So under the context of extrema, some things that we talked about that you should know about, right? That the derivative, if f prime of x is greater than 0, it's increasing. If f prime of x is less than 0, it's decreasing. So we learned about this. We saw that increasing and decreasing all comes from the derivative. Extrema occur where we switch, right? And in terms of extrema, there are a couple of types. There are relative and absolute. So you should definitely know the difference between a relative max, also known as a local max, right? Versus an absolute maximum. Again, absolute is exactly what it sounds like. An absolute maximum is the biggest thing. The biggest value is the absolute maximum. Absolute minimum is the smallest value. Everything else are relatives, right? So anytime we're at any kind of a little peak, that's a relative max. If it ends up being the highest point, then it's an absolute max. So when we did all those tests, the first derivative test, second derivative test, and we found critical points and all that good stuff, those were all finding relative extrema. It's just potentially some of them could be absolute depending upon what's going on. Okay, so we look for increasing or decreasing, and where it changes, those are extrema. All right, so they occur at critical points. And critical points are such that the derivative either equals 0 or the derivative does not exist. So that's how we defined critical points. So there are places where the derivative is 0 or undefined. So we take a derivative, we look for where it's 0, where it's undefined. Those are potential extrema. Keyword, potential. Not always, right? There are values that do not lead to extrema, not lead to maxes or min. So we have to test them some way, but they're going to occur at critical points. And so in terms of testing them, I'm just going to remind you that there's the first derivative test. And that basically is just, does the derivative change from positive to negative or negative to positive? And that's how you can tell if it's a max or min. If it goes from increasing to decreasing, it's a maximum. If it goes from decreasing to increasing, it's a minimum. Right? So there's the first derivative test, and there's also the second derivative test. And that's where we use the second derivative. And this one works for critical points where the derivative was 0, not undefined, but 0. And this one, if it's concave up, like a cup, then we've got a minimum. If it's concave down, like a frown, then we've got a max. Right? So there are ways of testing those as well. So be sure you know how to find extrema. Okay. So look for the derivative, 0 undefined, critical points, test them. This is probably becoming pretty, I was going to say easy. Easy may not be the right word, but you're probably getting comfortable with finding extrema because we've done it now many times over the last couple of weeks. Right? But the process of finding extrema is probably feeling a little bit better. Okay, so that's some stuff about extrema. The one other thing that I want to mention real quick, but we'll come back to, I'm going to make a separate little list, is if we're on a closed interval, right, we're guaranteed absolute extrema. That's from the extreme value theorem. Remember that you test those on the endpoints. I'll come back to that, but I just, for completeness, because some of you might be going, wait a minute, what about that? We'll get to that. All right, so there's extrema. Actually, while I'm at it, why don't I make this next list? Let's just talk about, kind of remind you some of the important theorems that we've hit lately. Okay, so we had the extreme value theorem. The extreme value theorem. Oh, wow, look, the sun just came out, which makes it so that you can't really see the whiteboard very well anymore. Hold on 1 second here. All right, so yeah, okay, so the extreme value theorem, this one is the one that guaranteed that we had maxes or mins. We had absolute max and absolute min if we had a continuous function on a closed interval. Those absolute extrema either occurred at critical points or endpoints. So just be aware, if I were to give you a function on a closed interval, check the extreme value theorem. See if it's continuous. If it is, then you know there are just a finite number of places where those extreme values could be. Check critical points and endpoints. Okay, so we had the extreme value theorem. We also had Rolle's theorem. That was the one that said if we've got a continuous and differentiable function, so not just continuous, but also differentiable on that closed interval, and those two endpoints had the same y values, then somewhere in the middle there is going to be a place where the derivative is equal to 0. Okay. That was Rolle's theorem. And Rolle's theorem itself is, but it was important because it allowed us to show or to prove the intermediate value theorem, or sorry, the mean value theorem. Now, the mean value theorem, again, all we need is a continuous differentiable function. That's it. But if your function is continuous and differentiable over a closed interval, then the mean value theorem says that somewhere in that interval is a place where the instantaneous rate of change is equal to the average rate of change. So the slope of the tangent line is equal to the slope of the secant line. Okay, so we hit these theorems along the way. Now, in terms of the theorems, I know a lot of times this starts freaking people out. Like, oh my God, on the exam, what am I going to have to do? Do I have to prove them? Whatever. I'm not going to expect that you prove any of them. Okay, I know that I did prove them. I showed you the proofs of each. That's because it's important to see where they come from. And I'm a firm believer in not just telling you something and going, yeah, this is how it is. I like to be able to justify it. And you should always be curious about that, by the way. In any math class, any science class, someone presents you with information, go, why? Why is that true? That's actually probably a pretty good thing to have about everything in the world. Right? Don't necessarily be skeptical, but be like, hey, you just made the statement, justify it. Right? Because I could tell you all kinds of stuff and claim that it works mathematically and be wrong, right? Well, that's why I showed you the proofs. So don't worry about the proofs. Some things for sure to know about. Know about the conditions that you need for them, right? The first one here, this needs to be continuous. These two need to be continuous and differentiable. The middle one, continuous, differentiable, and endpoints are equal. Like, know what's required for the different theorems and know the general results, like what it tells you, right? Those are the important things from theorems, not the proofs themselves, but the conditions, because you got to know when you can use it. So know the conditions and then know how to use it. That's really what you should key in on these. When and how can it be? Okay, so we had some theorems along the way. Those just kind of popped in here and there. So another big topic is concavity. That was another big thing that we kind of hit here. Okay, so concavity. Remember the difference between concave up and concave down. Concave up means that it would fit on a cup of some type, and concave down means that it would fit on a frown. In terms of how you tell, it's the second derivative. If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. So this is where the second derivative comes into play. It gives us an idea of the curvature of this. Where it changes are what we call inflection points. So those are the places where we go from concave up to concave down, or vice versa. And those are found exactly the same way you find extrema, except with the second derivative. So you look at the second derivative and you look for where it's 0 or undefined, and those are possible inflection points. But not always. They won't necessarily be inflection points. And also watch for those places where we change concavity, but we don't have an inflection point. We saw that happen over asymptotes, for example, where on one side it's concave down, on the other side it's concave up. Great example would be the butterfly function, 1 over x. It's concave down in the negatives, it's concave up in the positives, but there is no inflection point because there is no point at which we switch concavity. Anyway, so concavity is just another thing that we can use to help us get a feel for what graphs look like. All right, so that was concavity. We also looked at infinite limits. So these are limits as we go to plus or minus infinity. So just some things to remind you about here. Horizontal asymptotes. Okay, so horizontal asymptote, that's when we get a finite number as we're going to plus or minus infinity. We saw ways of finding it like that homework question that Ollie asked about earlier, the one with that square root on top, you know, like 11 plus 10x on the bottom or whatever. That's a good example of one, trying to find horizontal asymptote. So you can do it algebraically. But that just means that we get a number as we're going to infinity. We don't always, sometimes we go to plus or minus infinity, but sometimes horizontal asymptotes show up. Also, oblique asymptotes. Those are up the slanted line asymptotes. So the oblique asymptotes, watch for those. Again, those happen when the numerator has a degree 1 more than the denominator. So we did the long division. The long division then found the values, whatever that function was, that line was that we approached. So oblique asymptotes sometimes happen, and that came up in the infinite limit section as well. So in terms of that, be able to evaluate infinite limits, determine horizontal asymptotes, oblique asymptotes, that sort of thing. While we're here real quick, this exam technically does not cover L'Hopital's rule. Okay, so L'Hopital's rule is not part of it. However, if you recognize you can use L'Hopital's rule, feel free. All right, you understand what I'm saying? Like if I give you some sort of a limit and it ends up giving you a form that L'Hopital's works on, feel free to use L'Hopital's rule. That's okay. I don't mind that. All right, just make sure that you're using it properly. Don't use it on things where you can't use L'Hopital's rule. Okay, so we hit infinite limits. And so with that, with infinite limits, with the concavity, with the increasing and decreasing, we kind of used all of that to draw graphs of functions. Now, I am going to tell you that on this exam, there will be a question where I give you a function and I want you to draw its graph. Now, I know you have access to Desmos and you have access to graphing calculators and all that kind of stuff. Okay, so here, I'm just going to get this on the record right now. If your calculus does not back up your graph, you are not getting points. Okay, because if all it just is, if I say, find the derivative, find, increasing, decreasing, concave up, concave down, and I make you do all that different stuff. And then you get a miracle graph. That's the proper graph, but doesn't back up your calculus. I'm not giving you any points. Okay, not because you're not using the calculus to draw it. Anyone can get on that computer and type in, draw a graph of y equals x squared minus 1 over, right? No, that's nonsense. I don't care about that. I want to see that you know the calculus behind it. Okay, so just be aware. I'm gonna be a hard ass on this one. If your graph does not match what your calculus says, I'm giving you 0 points. Okay, so my recommendation is don't draw the graph. Do the calculus and draw a graph that backs up your calculus, because I would actually much rather, and in this case, you will get points. Like let's say you botch something along the way. You're finding concavity, you screw up the second derivative. But if your graph actually matches what you found for increasing, decreasing, concave up, concave down, I'm giving you full points. I'm going to give you full points on that graph because it's based on what you did calculus-wise. All right, so does everybody understand what I'm saying here? And this is slightly different than how it would be face-to-face, because in the face-to-face, I would actually give you a portion of this test that has no calculators. That's where I would put this question, right? And so you wouldn't have those resources. So this is how I'm going to make sure that you don't use those resources, is that if it doesn't match up, 0, like no partial credit, none. You understand what I'm saying? So no miracle graphs, no miracle graphs. Make it follow what you found, okay? All right, anyway, so one of the things that you're going to need to do is use all of this to figure out decent graphs for functions. All right, so then the last section, the last bit of stuff that we did, I think this is 4.7. Yeah, 4.7 is where this exam ends. So the last thing is the applied max min. Right, so optimization. So optimization, these were exactly what they sound like, right? Get the biggest revenue, the smallest volume, the whatever, right? Where we're trying to get maxes and mins, but in an applied setting. So this is actually very related to the earlier stuff in terms of finding critical points and testing them and whatnot. Now, these are also word problems, kind of like related rates, which means you have to find an equation for what you're trying to optimize, right? Like if they say, find the dimensions of the thing with maximum area. Okay, cool. Find a formula for area. You're trying to minimize cost. Okay, find a formula for cost, whatever it happens to be. Once you have that equation, make sure it's only in terms of one variable. We see a lot of times that there's more than one, but there's always a constraint. There's always a restriction. There's always a relationship between the variables that are in your formula. Use that to substitute in and get it all in terms of one. because one-side equations in terms of just one variable, now you just differentiate, find critical points, do your thing. Okay, so it's another word problem. How you're going to know it's an optimization problem is, again, the wording. It will tell you, just like with related rates, right? Related rates, you're always looking for the word rate, the word per, things like that would trigger related rate. Keywords for applied max-min problems, for optimization problems: optimize, best, smallest, biggest, least, right? Any kind of word that makes you think biggest or smallest, that's going to be, ooh, I'm trying to optimize. So with these, again, you got to read carefully, draw pictures, get your information down so that you can figure out the equation. Always look for, what am I trying to optimize? Create that equation, get it in terms of one variable, and then do your thing. Okay, so that's what's going to be on this exam. Right? There's a lot. There's an absolute lot of stuff here, and it's all application, right? And that's kind of how this class played out, right? We started with setting the table. We got all the different rules and everything. Then we got to derivatives. Here's how derivatives work. We learned all the different rules. Now we're starting to use them, right? And so this one's definitely an application kind of test. All right. So looking at the clock, we have about 15 more minutes, and I'm more than happy to talk about anything you'd like. So as we kind of went through this, you might have hit some subjects where you went, ooh, I'm not really sure what that means. Let me know, and I'll be happy to talk about any of it. Or if we're at a point where we are feeling okay, we can go ahead and call it a day. So with that, what would you guys like to talk about? All right, so I'm getting overwhelmed with the number of questions.
I have a question. For
Yeah,
I
sure.
know it's not for this exam, but for our final, because I know we have next week off in this college. Do you have a study guide for our final that we could do next week, or should we just go through the past homework problems?
So I don't have a study guide. I don't usually do that kind of thing. I could potentially make one up, but I definitely won't have it by the end of this week.
Obviously not, but just sometime in the middle of next week while we have a break.
Yeah. Let me think about that.
Okay. Yeah, I know if you don't normally do it, that's totally fine, because I don't want to give you more work. But I'm just saying it would be useful as a student if we had a study guide for our final.
Oh yeah, no, absolutely. If nothing else, something that you can use to help you kind of do that is go back and look at all the different quizzes and so on, right? Mm-hmm. And that gives you kind of a framework of the kind of the main topics, right? Like think about the quiz we just talked about. It was really, there was an example. It was an example from 4.1, and it was an example of the two kind of things that happened in 4.2. Mm-hmm. And I tend to do that a lot with the quizzes, is that I basically give you problems that are the key pieces from each of the sections. So quizzes are a really good measure, actually, of what's in there. It's just they're not going to be quite complete because of the fact that there are exams in between, and some weeks we don't have quizzes. But you can use that for sure to help you kind of build a little study guide. And you can use exam stuff as well in that. In terms of things to practice, you can always go back and practice more of the homework sets. Mm-hmm. And there are tons of that kind of stuff available out there on the interwebs, right?
Of course.
But I don't actually, I might have a study guide. I'll have to look.
Yeah, if you have an old one or one from another professor that teaches the same material, that's fine. Because I just kind of find it annoying to start a homework set that we already did and then just do 3 problems and then exit.
Okay. Well, let me finish one more thing. In terms of older stuff, I'm also a bit limited because I'm not at work. I don't have my work computer. And I don't have access to my work computer. I only have my laptop. So my laptop doesn't have nearly the bank of files in it that my one at work does. So I will look. I'll see what I've got. I think I might also even have a flash drive. Yeah, I might even have a flash drive that has stuff on it. So I'll see if I can find something. No promises, but I'll look into it.
Yeah, no worries if you can't. Thank you so much.
Yeah, no worries. And then again, I don't remember who it was on the chat. I think it may have been Bailey. I didn't notice. It just popped up and then left real quick. In terms of the exams, yeah, exam scores for exam 2 should be in there. There are a couple of you that are saying you're not seeing it. I'm going to go in and check and see what's going on. But if yours isn't showing a score, it should. I will look into that, and hopefully, if not later today, tomorrow, I'll make sure that they're all visible. So, all right. Yeah, thanks, Ayers. I saw you mention that earlier. Appreciate that. I had this happen with my other class once too. I'm teaching the second year calculus. I had a quiz like that where like half of them, the quiz scores didn't go in. So, okay, thanks, Mariola. So it sounds like the same thing's happening here. This must be a weird, quirky thing with Canvas or something. Happens every once in a while, but I'll make sure that I'll look into that. All right, anything else? All right, well, then with that, I'm going to wish you guys all a great couple of days. Good luck on the test. It will be like usual. It will open up at 8:30. It will be due kind of the usual time, which now I don't remember. I was at 10. I don't remember. Anyway, it'll be exactly the same setup as always. I will be on the computer in our usual class Zoom meeting. So if something comes up, pop in, ask me a question, and I'll still be available. And I'll be available. I've got office hours today and tomorrow, as always. Okay. So with that, have a great couple days. Good luck on that test. And if I don't see you, the next time we'll have class is a week from Monday. So next week we're off. All right. So it'll be a while, but be safe, have a good break, and I will see you guys all in, I think, December. All right, so see ya.